I remember you were asked what's the best way to draw a circle at a Microsoft job interview. What's the answer? Um, so in that way that Microsoft job interviews at that time, uh, were asking questions. That question was I would consider a particularly knowledge based question in that if you're not an expert graphics programmer, you wouldn't know the answer to this question, right? Uh, but the problem with that kind of question, as you might expect, is that it's highly temporal. So the best way to draw a circle back then is absolutely not the best way to draw a circle now. And the reason for that is because in the old days, no multi-threading, right? Everything was single core for what Microsoft was targeting. No floating point. The floating point units were very slow at that time, and sometimes they didn't even have a floating point unit, so it would have been emulated. And three, no wide instructions. So, today you wouldn't dream of trying to do something fast without a wide instruction, right? All your instructions should be single instruction, multiple data instructions if you're trying to do something fast, right? That's how graphics cards go fast. That's how, like, the CPU goes fast. Is lots of cores doing wide instructions. So none of those things were true back then. In fact, wide instructions were not even a thing that were contemplated on the PC. I think they did exist in other architectures, potentially specialized architectures, and they were, at least I know for a fact, they were contemplated. I just don't know what they were shipping in necessarily. But Intel hadn't even announced plans to do something like that. So with the very important caveat that it is no longer an answer you probably should ever be thinking about, because it is wrong now. The way that they wanted to see you do a circle was that, obviously, if I give you the center of a circle and the radius, it's trivial to find one pixel, right? I should probably just draw this out, but it's trivial to find one pixel that you could consider to be on the circle, right? And furthermore, it's trivial probably, to find four. And, rather than try to just state it and describe it really elaborately here, I'll just draw it for you. The reason for that, of course, is that on a pixel grid, if I say that a circle is somewhere, so we'll call this the center of the circle, right? Then I know that whatever pixel the center is because the person had to tell me that, right? So the person had to say that this circle's center, right, is like, let's say, CXCY, right? So they had to tell me what that is, and I can look that up in the pixel grid right away just by doing a multiply and an add, right? By, multiplying the stride here and do an add here. I'm going to get this pixel, I wouldn't say for free, but pretty close to free, right? And then, because you also have to give me the R, right, the radius of the circle that I'm trying to draw here, I can also find 4 more points for free, right? Because I know this point is just going to be like plus R in the X direction, and I know that this point on the circle is going to be minus R, right? And I know that the same thing would be true on the y-axis, right? You know what I'm saying? So from the start, obviously, I can get sort of for free. I can sort of get the points that make a diamond in this, of what the circle would be. So the question now is, how do I just draw the actual arc, right? Now again, just to emphasize how not a good idea it is to do what I'm saying now, because this is only relevant on very old hardware that literally does not exist anywhere today, except maybe in some kind of like crazy embedded system in a very small space or something. I don't know. I don't even know if hardware like... I don't even know if there still exists hardware where this makes sense. So that's how old this is. So in order to draw the arc, what I want to be able to do is I want to be able to do something that does not require a floating point, and is not wide, right, and is not threaded. So all of the things you would normally do today to make a fast routine, I need to do none of those. In fact, I can't do any of these. And so what ends up happening is you say, well, okay, in order to compute the equation for this circle, right, I know that I have cx squared plus cy squared minus r squared equals 0, right? I mean, alternatively, cx squared plus cy squared equals r squared. I mean, it doesn't matter how you want to phrase it. It's up to us depending on what we want. But if we look at what's going on here, you can sort of see we've got two things that are a multiply, like cx squared, cy squared, and one thing that's a constant, right? So if we move around the pixel grid, this is changing, this is not, right? So it's pretty free for us to compute r squared or negative r squared and not have to do that work anymore. But now the question is, well, the cx squared plus cy squared part, what are we going to do about that? What's the easiest way to make this work for us, right? Now, to be honest, I don't really remember the exact answer they were looking for, but I'm just going to do a good answer here, and I'm sure it's either as good or better than what they were looking for. Interview questions, sometimes the interviewer doesn't know the best answer. I remember there was one Valve one like that, about quad trees, that I later figured out. I didn't get the interview question, but the person who typically asked it had told it to me. And I was later working on a quad tree, and I figured out, like, just because I was doing some stuff, and I was like, oh, actually, that answer is not the best answer. The best answer is actually this. But that's neither here nor there. All right. So anyway, looking at this, what you want to do is say, how do I minimize the cost of finding the pixels in here? How do I minimize the cost of finding which pixels this is closest to 0? Because remember, in this day and age too, these things are so underpowered, no one's doing anti-aliasing or anything like that either. So we're literally just talking about filling the pixels that make the arc solid. So we're not trying to figure out like coverage information or anything else that would actually require a little bit more work than what we're doing here. We're trying to only light up one pixel the whole way around, right? All right. So if you start off here, or actually let's start off on plus r for now, because that's just, you know, hey, positive. If you start off here, you know that cx squared plus cy squared is r squared, right? Because we know that this is on the circle. So that's just like a given that has to be true. And you know that it's true because since there's no y component, the x component of the circle is just r, right? And if the x component of the circle is just r, then this is r squared minus r squared, because that term goes away. So obviously this is on the circle. So what we can do now is change it around to say, if I'm already on the circle, I know that one of my neighboring points also must be on the circle, right? And furthermore, I know that those points, if I only wanted to draw the arc in one direction, I know that these points are the only candidate points that could possibly be it. Because I can never get further away from the center of the circle, then plus r, right? That I know that I'm already on the outside of the circle. So I can go up, or I can go left, or I can go up and left, but I certainly couldn't go right or up and right, right? This is not allowed. So what I can do is rephrase the question of which direction to go. Also, by the way, I should say one more thing. Branches, not expensive this day. Why? Not out of order. So the processor just went in order and retired one instruction basically at a time. I don't even think they were superscalar. I don't know what the first superscalar x86 was, but this is like, this is like 286 era, right? A style question. And so 486s, I think, were brand new. Some, like, a fair number of people had 386s, but the interview questions were all from, were a couple years old, right? So they were all, 286 era questions. So I'm pretty sure the 286 really wasn't superscalar, so I think the 286, had no branch prediction. I don't think. I think it just executed the branch and then stepped to the next one, right? So I'm pretty sure, although, it's been 30 years or whatever it's been. I don't even want to know what it's been. 20 years? 25 years? No, I think it has been 30 years. Jesus Christ. It's been 26 years. 27 years. So we're also talking about not caring how much branching there is, because branches are not more expensive than other instructions. They're the same. So normally, again, while you were thinking about all this stuff, you would also not want tons of branches sitting around inside your code. Not true anymore. It's just another thing to consider back in these days. It's just another instruction. So a branch that saves you computation is probably a good idea, because branches were probably cheaper than an integer multiplier or something, right? Anyway, so if you look at what you're trying to do here, you're trying to pick which one of these three is going to be the point that is most on the circle from our current location, right? And so what we can do is say, well, if I were to compute this equation at these 3 points and just pick the one that is closest to 0, so the one with the least error, whichever one has the least error must be the answer. So if we went ahead and said cx plus 1 squared plus cy plus 1 squared minus r squared equals, error 0. Cx plus 1 squared plus cy squared minus r squared. And I don't know why I'm saying c. This entire time I've been writing c, I just mean x and y. C was supposed to be the center of the circle. I'm sorry. I got carried away. Pretend I didn't say that. There you go. This is what I meant to say. I forgot I don't know why I was I picked up cx in my head and ran with it. That's why I'm bad at writing math out. And finally, x squared plus y plus 1 squared minus r squared equals e2, right? So if you look at what these equations come out to be, you can see that the terms are reused a ton, right? So really, I know that x squared and y squared I already had to have known, because they were the location of they were what I accepted last round, right? So I know x squared and y squared, so I kind of have 2 registers I could keep, which is my px and my py squared. I don't know, I don't know what you want to call these, but I can keep these around and just use them here. So really the only thing that I'm trying to figure out is the new values of these, right? So I can keep those around if I want to. It depends on, again, the processor and specific things, is whether or not you'd want to, how many registers it has, whether you can, how quickly you can multiply an integer and all that sort of stuff, right? But, so what you can see here is if I just compute these three equations, I then know three error terms, and I just have to pick whichever one is smallest. So I compute this one, and more specifically, right, I just compute x plus 1 and y plus 1 squared. That's really all I needed to compute. I compute those two, then I add them together and subtract r squared, that's one error. Add just x1 plus the old y squared minus r squared, that's a new one, right? But I don't have to recompute this because I already computed it. Same down here, I just add the old x squared to the new y plus 1 squared that I already computed up here, subtract r squared, and off we go, right? So then the absolute value of each of these three, whichever one is least, that's the pixel that I need to pick, right? That's the pixel that I would go to. So we can get more out of this by oops, I didn't mean to change the zoom there. There we go. I can get more out of this by, do I have a space bar? Oops, nope. Is there like a key on here that is equivalent to the space bar? I should map one. Oh, okay. There's like some buttons on this pad. If one was equivalent to the space bar, that would be pretty baller, but there isn't. I'll map one maybe. So what we can do is just create a loop that goes, hey, which of those three is smaller except that movement, right? Now, if you want to, you could also say, and I think this was part of the question perhaps, so you could say I don't want to check this, meaning I only go up or over, right? Now, they didn't tell you any of this stuff for the question. They just said draw a circle, but I think they might have said you don't have to do single pixel diagonals. So you can do ones that are fat, you know, because it's hard to say which one you want when you drawing a circle when you're talking about sloppy pixel drawing like this. It's hard to say which one you want, right? So really, you can probably say that this one is not there. What that means is that when you do this, you just have one if. It's like if, abs E1 is less than abs E2, select this one, else select that one. So you're just a loop that just does that and goes, right? Okay. So you only need to do these two to draw this first part of the arc, right? And you can, imagine that going up this way. Now, if we look at this a little more closely, we can also ask some other questions about it. If you looked at these equations, you could also see that, well, we know what this is if we expand it out just using, if I just use sort of the math you learned in grade school, right? X plus 1 times x plus 1, right? That's what this is. If you use the distributed property to expand this term, you would get x squared, right? On one side, you would get 1 squared on the other side, which of course is just 1. And then on the inside, you would just get 2x, right? You can kind of see, what's going on there, right? So if you know the old, if you knew the old x squared, you could really get away with just doing 2x plus 1 is really what all you need to add to it to compute the new term. Does that make sense? In other words, I started out in the old days, I knew what this x squared was, and registers become a problem back in the old days. Remember, there's very few registers, so how to actually, he didn't have me write this in assembly, and because I didn't know assembly at the time, really. If you really wanted to talk about how to do this fast, you'd need to write this as assembly. And I would have to start thinking about register usage, which back then, I don't even remember how many you had. You had at least 4. I think you had A, B, C, and D, X, AX, BX, CX, and DX, which were, I think, 16-bit registers, just like they are now. And I don't think you had EAX. Like on the 286, I don't think they had extended it to 32 bits yet. I think that was like the 386 that did that, maybe. I don't know, maybe the 286 did. So I don't know how wide these registers were, how many bits they were, but I think they were probably 16-bit. But don't take my word for it. So anyway, if you look at what happens here, you can see that in the actual loop itself, we can get a lot of efficiency. We don't actually have to compute these equations whole cloth, because if we just store what our laxed x squared was, right? So we store our old x squared, our old y squared. You know what I'm saying? If we just store what those are, we can compute the new ones just by adding to that, right? We can add 2x plus 1, and we can add to y plus 1 to get the new versions. We test those versions, right? And then just accept that value as our as our old values for the next run of the loop. So that gets us out of ever actually doing an integer multiply, because the 2x and the 2y are actually shifts, right? Because if I want to do, oh wait, there's just one thing. These are always, yeah. These are always positive numbers, right? Because like I said, I'm going to show you why that's true in a second. Like I said, I'm starting over here, right? So the x and y numbers are always positive, so I don't have to worry about any 2's complement or anything else like that. I'm just drawing in the positive quadrant of the circle. And in those days, graphics always went downward, so technically you might really, if you were thinking really old school, it's actually these 2 pixels we're testing and we're going this way. I'm drawing it that way because that's how we've always drawn circles, and that's how our coordinate systems always have worked on Handmade Hero. So, but that doesn't matter. The point is just whichever way your graphics system thinks is positive, that's where we're going. We don't want to deal with any 2's complement issues. We just want it to work, right? And we don't want to think about sign extension or anything else. So if I want to multiply something by 2, right, I should just be able to do that bitwise. I don't have to actually issue an integer multiply, because it's the special case of multiplication by 2. And since we're in a binary number system, right, I can just move it. And I think that would work in negatives anyway, but before I started talking about that, I wanted to make sure I knew what I was saying in terms of. So we're always in positive, so we don't even have to think about that. That's not relevant. So we should be able to do this entire thing without actually doing any multiplies at all, right? We can just do shift add, shift increment, test, and go, right? Okay. So if we go one step further into Ridiculous Town, we can also think about, and I can't quite remember, because it's been a long time since I've looked at this sort of thing. Yeah. So if you look at how this equation is being run, you're always doing and this again just depends on whether you've got the registers for it or not. If you want the y squared term, if you look at what happens with these equations, right, where you do, you're always computing something of the form x squared plus y squared minus r squared, right? And the way we're ending up computing this entire equation is with what it amounts to be like some ox, old x squared value. O is probably the wrong thing to do there. Let's do previous x. We're using some previous x squared value plus, right? We want to do the 2x plus 1, right? Plus some previous y squared value, because it would be the same, minus r squared, right? And we want to compute, well. Or we're fundamentally doing one or the other of this, right? Like that's what we're doing. Make sense? Because there's really no other operation that we could do. We're just doing those two, and then we're testing which one of these is greater. So in here, if we were to reorganize these terms, what you would see is that they're actually the same darn equation, right? If I move this py out to the head end, then what I see is this, right? It's the same exact equation. The only difference is that. You know what I'm saying? So this right here is actually the only difference between these two values. So what I can do instead of all the other stuff that I was about to do, right, is I can just keep that if I want to, because I only need it. That's the only value I need. And then look at what these two values do, right? Now, it's easier said than done because the problem is you have to update it. So you need to figure out a way that once you change the x and the y, you're going to actually get the new value that you would have had that was on the circle, right? Does that make sense? So looking at these two values here, we can say, well, you know, the previous point that we were at is going to be px squared plus py squared plus 1 minus r squared. That was the error on the previous point. We're going to add 2x to it or 2y to it, and that's going to give us our new error. We just want the minimum one, right? But assuming we just go, well, look, we're just always trying to be as close to the circle as possible. We don't really care about knowing anything else other than what our error is. So really all we need to store for this entire time is just error, right? We just need our error value. We need our x value and our y value. And these are just necessary for plotting, right? And, well, and computation of these two values, right? So we should actually be able to get away with maybe only 3 registers. By storing this value, every time we go, we shift x up by 2, we shift y up by 2, we add them, right? We see whichever is the lesser error, and we just write that error back, right? Then we take the new x value, either the plus 1 x or the plus 1 y. Well, I think it's actually minus, probably in both cases. Now I think about it, you probably want to instead of going plus both ways, now that I think about it, actually implies you start here, right? So maybe that's fine. I don't really care. Doesn't matter, just point being, pick one so that the pluses are the same, so that we don't have to compute a different value. By the way, as I'm working this through, I'm thinking that actually the interviewer didn't know half of the things I'm saying here, but that's beside the point. So we should be able to do just the error, compute it this way, write it back. Then we draw whichever point we selected and continue the loop. Make sense? Now, obviously, the next question is, well, at some point, you're going to have to switch to going back down, right? Like, you're going to go like that, and you're going to have to go back down and all this other stuff, right? How do we deal with that? The final thing you need to think about in order to make this routine fast, again, in those days, it is not how you would want to do it today. But if we look at what's going on here, what you can see is that as we move around the circle, it's really 8-way symmetric if we want it to be. I mean, a circle is an infinitely symmetric shape. I can draw any line through it that I want, right? And it will be the same after you mirror it. So if I split, like straight down the middle, for example, I know that every point I draw here, I could have just drawn on the other side of the circle just by negating the x around the center, right? So if I just always think of the x as like plus x, I could also just draw negative x, the same point, right? So that means I really, and I could do the same with y. So that means I really only need to draw one quadrant of the circle, and then I just mirror, right? Instead of drawing the x, y's I come up with, I draw the plus minus x, plus minus y, right? So all four are combinations. Plus x, plus y, minus x, plus y, plus x, minus y, plus, oops, minus x, minus y, right? So that gets me out of the business of ever having to care about going downward. But if you look, there's one more symmetry you can do, and I drew it here, and that's diagonal. Every point on this circle that I draw xy, I could have also drawn yx, right? Because it's symmetric this way as well as that way and that way. So every point could have been reflected about this line, which turns y's into x's and x's into y's, right? Does that make sense? So I can also only draw an eighth of the circle. Make sense? So what I can do is, rather than do all of the work that you might think of for drawing a circle, I can literally do something like while, x is, or I guess we're less than or equal to y, do that if e1 less than e2, it's like this. So you get the whole drawing of your circle down to that. And then a big old honking right pixel, right pixel, right pixel, right pixel, right pixel, which are like memory pokes into those addresses, right? Make sense? So, essentially that is what the interview question, and you can see, so let's say you interviewed me today on anything related to this. Because my mind already has gone through this work, I can just do it, right? And, that's the optimal result for an interview question like this, is to see the person just, go off and, show you all the possible things you could have done. But, again, it's kind of a worthless interview question in my mind, because this is called a Bresenham-style algorithm. Bresenham-style algorithms are algorithms that draw from a known location based on minimizing error as it steps along pixels. You can do them for lines as well, and other shapes. Pretty much anything that has an implicit form can be drawn Bresenham. If you can find a starting point on that shape, then the Bresenham version of the algorithm is to remember what the error is at the point that you're sitting on. And then as you draw, all you do is look at the 2 or 3 candidate points that you want to examine and say which one of these has the least error, and you go to that point, right? So really that's it, right? If that makes sense? Let me see here. So yeah, if you were to imagine, I don't know, we're kind of in for a penny, in for a pound here. Should probably upload this as a separate video. Let me just give you a... So let's just say, for sake of argument, right? I don't know what we're going to call... Oh, we got a test directory here. I know those are pings or something. So in the Handmade Mist directory, let's just say that we've got a thing that's like... like a Bresenham circle routine, right? So if you imagine you're back in the old days, let's just say we have a pixel grid, right? So there's a pixel grid in here, and we're just going to make it up like the way that it was back then, where there's just a block of memory that you write bytes to, and that's the entire thing. Do you know what I'm saying? So basically what you want to do is say, all right, let's say we have a char here, we have pixels, and our pixel grid is just going to be like some kind of a size here that we are comfortable printing out, like 64 by 64, right? And they'll all start out equal to 0. And then what we're going to do is we're just going to draw our pixel grid at the end of the day and then exit the program. So if I were to do that, what I can do is say, all right, here's our output. We're going to say that our x is 0, our x is less than 64, right? In fact, I can just do this. Okay. So now what I want to do is just say, look, if there was something in this pixel slot, like whatever it is, and we'll do XY because that's just, you know, a little bit more memory order friendly. If there's something in that slot, then what I want to do is say, like, draw something there that we know. So, you know, it would be something like a star, let's say. Oops. And if there's something there that we don't know, then, or rather there was nothing there, maybe we just print a dot, right? So we can kind of see what's going on. Every time we get to the end, we print a carriage return, right? And so maybe here I can also do like, all right, pixels, you know, 32, 16 equals 1. Okay? So if I come back here and I will go to the build directory, let's say, and I just run a CL on it. So I just say CL, you know, handmade misc bcircle.cpp, and run it. What you can see is that it prints out our pixel grid, you know, quote unquote, right? Now, we're super eccentric here is the only problem. Like, you know, this is not a square font, so it's going to be like an elongated kind of nonsense, but that's just how we'll deal with it. What I can do to compensate for that a little bit is maybe make this a little bit smaller. So it's 32 by 32, and we'll plot the middle, you know, middle point, right? There's our nonsense. And so now we're going to try and draw a circle, and the circle is going to be kind of an oval because our coordinate system, you know, is stretched, right? But we want to draw our circle. So we want to be able to specify this, and again, no floating point here, folks. And these really should be shorts. So, you know, it's really this. It's like unsigned short CX, unsigned short CY, right? You know, we could leave them signed too if we want. It doesn't really matter because there's the pixel grids back then were like at best 640 by 400 or 40. So you didn't have to worry about large numbers. So, you know, here we've got two short values. This is going to be the center of our circle, wherever that is. And so let's say we want to draw one, you know, that's centered at 10, 12. And we want the radius of our circle to be, you know, 6, right? So now I need to do my drawing loop. Like I said, I want to do a drawing loop such that it starts at a certain x and y that I know and then goes up so that the x and y values will basically cross at some point, right? And that's how I know that I'm done. So I want to do something where like my x offset and my y offset are like I'm not sure how to say this. So there's a couple different ways I could do it. One is I can try to compute a value that I stored that I know when my x crosses it, I've gotten over there. Or if I'm based around 0, I know that it's just when the two flip. So it's just like when x is less than or y or something, right? So if I wanted to start off in that scenario, what I would first do is say, well, I know that the x location that I'm starting off at, right, is going to be like I wanted that X location to be negative, right? Because I wanted to start on the side where I'm always doing plus. I'm always doing a plus direction. So I would like to start off with yeah, I think that's right. So I want to start off with this as being the negative r, right? I'm going to base it around 0, and then I'm just going to draw with an offset. So I'm going to base it around negative r, and then the y I'm just going to base as 0, right? And then while these two, while I haven't actually crossed over yet, so while, y, and you can see that x is going to be negative here, so it would always be, so I need to negate this in order to do the check, right? Meaning I need to make sure that as I step, I account for the fact that I'm negating as I go. Now, we may be able to optimize all of this stuff further as we start to look at it more, but just like for now, we're just trying to get the basic sketch in. So then what I need to do is say, all right, I need to compute my two errors for starters. And again, we might be able to simplify a lot of this, but we're just going to start with the basic version of it. And so for the error, if I look back at what we were saying here, right, what I needed to do was figure out if I start with the previous error. So like whatever the previous error is. Where are we here? Yeah. So if I start with whatever the previous error was, right, then I know that I need to, because the x squared plus y squared minus r squared is whatever the previous error for this thing was. The plus 1 plus 2x is what comes out of me computing the new value. So first, I need to take my old error and I need to add 1 to it to get that part of the value, right? And then I need to go ahead and really, I should probably write this routine doing the whole computation correctly and then do the optimized one to show you the full thing. We should just do this whole thing sometime as an entire episode. But anyway. So what I want to do here is say, all right, I need to compute the updated version. So I know it's the old error, which I've already incremented by 1, plus the 2x, right? And then the new one is the old error plus the 2y, right? And now, like I said, I don't actually want to do any kind of multiply here. I just want to shift, right? I just want to multiply it by 2 by shifting. So then what I want to do is say, well, I need to know which one is, for the absolute value, whatever that's going to be, right? I need to know which one's absolute value is greater, right? And I'm trying to think if there's some way we can avoid that, but I don't. Because it's a circle, you might be able to know that you'll always be slightly above or equal to on a y step and slightly less than or equal to on an x step. So I want to say that because, like, if you're going this way, if you step inside, you're almost always going to be less. And if you step above, you're always almost going to be more. So I want to say you could do something probably like this. I want to say, but we'll have to actually analyze that a little bit more, right? But I think you might be able to get away with not actually looking at those values, right? So anyway, we're going to do something like this, and then we're going to record the old error as that thing, right? So if in this case the old error was if in this case the x step was going to be the better, we'll take it. If in this case the y error was going to be better, we'll take it. And when we actually do the step here, we need to update our x and y values, right? I don't know why I'm writing these in lowercase for some reason. It's not really how I do things. There we go. So once we have those recorded, we need to do, this or that, and then we're good to go. So finally, we need to do a plot here, and this we will do a little bit differently later, but for right now, we're just going to do it this way. So we're going to do yx here to plot that particular pixel, and off we go, right? All right. Is that it? I've probably forgotten a lot of stuff there, but we're just going to see what happens. Yeah. We start out with an error of nothing because we're assuming that we're directly on the circle for our definition of the circle, right? And this was backwards. I actually meant that. All right. So I forgot one more thing. There we go. All right. So we are accepting the step in the wrong direction because this was a minus, right? The x is moving backwards on the actual, I'm sorry. No, they should both be moving forwards. Why are we getting that plot? Oh, right, because y goes down. This is old school. Y goes down. We're fine. All right. So what we now need to do is plot all the other points that I was talking about before. We need to plot, every single one of these. So in addition to doing this, which is, taking each of the possible locations into account here, we also need to do swapped versions, right? So this draws every one of our coordinates here, right? And now we've sort of got our circle, although it looks like we've got one error in the... Oh, no, we don't. That was just this. Right? So now we've got our circle, but we don't really have the plot of the initial pixel, right? And so what we may want to do is change this around to say, let's start plotting the thing that we were going to plot in the first place, right? And hey, look, there's our circle. Ta-da! So looking at what happens here, right, you can see that we can continue to make this even more ridiculous as we go and reduce the instructions even further. I don't think there were any conditional moves at that time, but if there were, this becomes branchless in a sense. Well, not really, because you'd have to do too many of them to probably make it worth it because of the plus x plus y. But anyway. So if you look at how simple this is, right, it requires just two shifts, one negate and a check, and then one equals and one add, and that's it. This part right here is a little, extra add to do the ink, so it's a little more cost than it should be. This part is incredibly expensive. So the question is, what can we do here that would... is there something we could do here that would make it less bad, right? And there are a couple things we could do, certainly. And one of them is to just say, well, if we were to change this pointer to just point at the center to begin with, right, we could get rid of the CY, CX nonsense, right? So if we did, let's say we've got a, like a cursor pointer, and we make the cursor pointer be pointing to specifically the CX, CY location. Then when we drew this, we would be able to just use X and Y. So if this was a pointer to, oh. Don't know what I was doing there. Good thing those were equals, huh? So if I do something like that, and then I say, okay, here's my cursor. Oops. Oops. Don't ask me what that typo was about. I want you to cast that for me. Well, you know what? This is the step I was going to do next anyway, so we'll just leave it at this. So let's say we've got our cursor pointer there, right? And then what we need to do is we want to write to a particular location in it, right? So I know that I want to do this location, but I know that y needs to move by whatever the stride is there, right? Right? So each one of these y values here now has to be, each one of those y values has to be multiplied by the width in order to go the right number of pixels, right? So we really need like times width after each of these y values. And remember, these x values are effectively y values when they're, you know, in this, when they're being used in this bottom half, right? Because we're swapping the two coordinates. So if we draw, well, I must have missed somebody there. I did. Sorry, I removed a negative. Right? So now we're down to cheaper, but we've still got this integer multiply here, right? And the integer multiply is not fabulous. But if you look at the structure of each of these, you can see that we actually don't need anything other than, right, a y value times the width and an x value times the width, right? Because that's the only value we're actually summing up there in order to get our 8 quadrants to come together, right? So if we were to track that value specifically, rather than the other values that we're tracking, we could simplify this even further. Now the question is, how do we keep that from getting to be too many registers? And again, I don't really remember how many there are. There might have been 8. If you didn't need to access the stack. So if you, well, no, you would always need to store the, no, I guess if you didn't have to access this, but you need to store where the stack is so that you can pop it. So you would need that. So I think you'd at least, you'd probably only have 7 registers at best. I don't know if it would be 6 or 7, how many you'd have. But if you look at how many we're using here, we're using 1 to store EP, right? And we're storing 2 more for X and Y. So we use 3 registers already. And then we probably need a 4th register at least for computing these values here. Probably 2 registers. So we probably need something like 5 registers. So we probably only have 2 registers left to store the pointers at best, right? And so the question is, what could we do here? Is there any way we could make this do less multiplies by storing 2 values instead of 1 value for cursor? Right? Now, all of these, plus x minus x plus x, all of that's pretty cheap, right? Those adds are not that bad, and we know we have to track x and y, or do we? I mean, I guess we don't necessarily, but it would seem pretty hard to not, right? So what we really want to know is there any way we can speed up this multiply by width here by doing something else? By tracking a value that's like times width or something, you know, like what can we do to fix this, right? And to be completely honest, I can't really think of it offhand. Anyone got any ideas? I also am not sure, we didn't really check this, right? So, you know, we may have to do some more work here because that is actually what we want. I don't know what that's in. Maybe math.h? Yeah. Looking at it though, that's the same. That looks the same to me. So this is the only part I'm not sure about. Because I feel like we could probably do this a little bit better than we are. And I guess if we were, because we would need the base value is the problem. I don't know. I don't really know how to simplify that down to something that only takes 2 slots. I mean, I guess, well, no. Yeah, I don't know. X shift up 5? What would X shift up 5? Well, yeah, I mean, assume that this, you don't know what that is, right? Like, assume that that's that. Or something, right? Or, you know, this is more accurate to what the situation really was, right? So you can't use shifts anywhere. Yeah, the problem though is if you do, like, if we do any other kind of thing, we can't get the symmetry out of it, right? If we just have the pointer that we're using to write pixels to, how do we generate the other locations, right? Because it starts to become more expensive to do that. So we really, because you really want to get the symmetry out of it, because it divides the cost of the routine by 8, right? And so, yeah, and someone was said store the X with and Y with pointers, you increment accordingly every run. That's what I was thinking, but that's more than 2 registers. Because you still need this value. Right? Because you need to be able to negate the Y. If you stored 4 of them, you could do it. But if you store 2 of them, you can't flip this thing. At least not that I can't think of how you do that flip. See what I'm saying? So there you go. But anyway, that's something to ruminate on. That's the routine, right? And this is I think probably, I don't know if it's quite the best answer. We might be able to grind it a little further than this, but this was, I think, to be honest, I think this was actually better than the answer that the interviewer sort of discussed at the end of the question. We're probably better than they are at this point, but that's not surprising, right? It was just some random dude at Microsoft. But that's effectively what it is, right? Someone's saying, I'm thinking on 68K terms where they're a bit more... Yeah, 68K had a lot more registers, like twice as many, right? I want to say. The x86 was really register starved. That's just... You know, everyone knew it. nobody thought it was good that there were so few freaking registers on the thing. But yeah. So I don't know. I feel like this part right here is the part we can really improve. This part's looking pretty tight. We may be able to optimize it very slightly, but it's pretty darn good, right? It's like 2 shifts, 2 adds, a compare. Well, 1 add, 2 shifts, 2 adds, a compare to get the step. And so, yeah, like maybe we can get one of those out of there. But so here's a question, though. Here's a question. We're starting to get like way better, I think, than the answer that the person gave at the time. If EP is added to each one, then do we ever actually care? Like this is an affine transform of the equation. But we don't care what the affine transform of the equation is, because the affine transform of the equation just moves everything in space over by 1. So in theory, we should be able to do this, right? And get the same circle. I guess not. That's a different circle. I guess because of the negation here. Yeah, that's true. It's moving it this way, but we're flipping one of them. So I guess I lied about that. So never mind. I guess, oh, well, you know what, though? So if we're only ever testing negative E0, I suppose you could negate this. Potentially. You might be able to flow that through a little bit differently. Yeah, I'd have to think about that. But no, I guess, I don't know. You can't even get rid of that, so I'm not sure. That might be just about as good as it's going to get. It's this negation that hurts here. Because otherwise you could just clip out EP entirely, because this would let you know. It's worth asking the question, can you just compare in some other way so that you'd only have to look at these two here? And I'm not sure about that. So there might be a little bit more, right? There might be a little bit more we can get out of that. Yeah. George asked the same thing. Can you get rid of the EP plus equals 1 line? And you could have if you didn't negate. Because negating this means that the +1 actually becomes a -1 for the E0, right? Which is different than it is here. So this negation is what makes that not possible. So, yeah. So what if we changed our thinking on this just a little bit? So what if we said, look, for this whole thing, we're just going to negate the x value from what it was, right? Like we're gonna flip the x value. So if I just negated x the whole way through, it would look like this, right? Probably. No, that's actually still that. Something like that? Is that wrong? Yeah, that's totally wrong. I need to do that a little cleaner. So if I want to negate x here, oops, I know what I forgot to do. There we go. There we go. So if I negate x all the way through, then it looks like this. And I still draw the same circle, right? Is that same circle? Yeah. And so negating x all the way through there, does that give us any options that we wouldn't have had otherwise? I don't really think that it does. So applying this negative here, if we wanted to work it back through, so if we said we wanted that, E0 now has to be computed as negative, right? And I guess it would have to be negated in here, though. Right? But we can do that if we want to. So yeah, that ends us up like this. That doesn't seem to really do anything good for us, though. I can't see how that would help, because we still have the negation in there. Because it's EP, it still is EP plus 1 or EP minus 1, right? Depending on the circumstance. So maybe, yeah. I don't see it. I don't see how to get rid of the plus 1. Because no matter what we do, it seems like that plus 1, right, is just, it's not, it's not going back in here. It's always going to have to be like a minus 1 or a plus 1, right? Like I don't see any way we can eliminate this line, because this always wants to be the other way round. Like it always wants to change whether you're going plus 1 or minus 1 based on the stepping here. I mean, I guess what we could say is if we just wanted to change the direction that x was going just entirely, though, you know, would there be some way for us to do that? I mean, if we started, oh. Wow. So here's a mind bender for you. Since we don't care which part of the circle we compute the x and the y on, what if we reflected it so that the x value is actually drawing on a different part of the circle than the y? If we say that, right, and we change this to just be based on like some kind of an r value, then I think we could get rid of it. This test, knowing when you're done, does seem hard. So that part I'm not sure about. One thing we could do, and this is a real wild shot, I don't really know. One thing we could do is this. I don't think that's going to work. But then we would literally just be doing this, I think. So we're actually not even ever really drawing we're not following a path along the circle. We're just starting X at the origin and Y at the origin, and we're just stepping along two separate circles, seeing which step we probably should take first. I don't know. I don't know if this will work. This condition, I don't know. Yeah, because I don't know what condition to stop on that's not going to require us to compute some other value is the only problem. Because at that point, you kind of need to say, look, while X is less than like half of R or something, you know, it would be like this. And that requires like another register, you know? All right, I screwed up something there. But you know what I mean, right? Like that. So let me try that. Let's try that and see if we can get that to work. That's a real mind bender. So basically what we're saying there is, okay, if the step on X would produce less error than the step on Y, even though we're stepping them on totally different places on the circle. Let me look at that equation again. So if I wanted to step X and Y, and I just wanted to eliminate the +1, right? The problem there is in the absolute value of E1 and E2, right? Otherwise, we could just do it. But the absolute value flips around which way that +1 is going. Now, if I want to step on the circle, I feel like this should work, though. I feel like we should be able to do it this way. Why didn't that work? I wish I understood quite why that didn't work. I guess that's because there needs to be a differentiation between them, otherwise they're both doing the same thing. Let me look at this one more time. So here's the original, right? And what we're actually doing here when when we're computing this, the only difference between these two paths is that the X part is getting that negation, right? And the two steps have to do something different, but I guess they are because one's X, one's Y, right? Since I should be able to flip the X coordinate just fine, the thing that's a little confusing to me is why I can't change it to computing directly off of the X, and directly off of an X0, Y0, right? So let's straighten out here. Here's what I'm saying. So let's suppose that we always wanted to have X step in a way that would increase the error on the top side of the circle and Y. So in order to do that, let's say we start the Y this way and we start the X this way, right? Because in both cases now, we're always going to be pushing the error when we step, right? We're always going to be pushing the error out further as we go. You know what I'm saying? And I feel like, wasn't this a minus minus x before? Why is that still a plus plus x? Huh. I guess we inverted that at some point. I don't remember that. But anyway. So, yeah, drawing the circle this way, it feels like we should be able to say, like, look, take a step here if the error would be less than taking a step here. You know what I'm saying to you? But I guess it's because the error doesn't track properly. It's a little mind-bendy for me. I'm not sure how to analyze that properly, right? It feels like we should be able to get those down to both going the same direction, but somehow we don't. Somehow we aren't able to. And I don't, while I understand maybe slightly just in terms of rote equation manipulation why that's happening, I don't actually, my intuition is failing to grasp it, which bothers me. So like I want to be able to intuit why that can't happen in a way that's a little bit more straightforward. Because right now I'm having trouble with that. If you get rid of the EP plus, what you're really asking is x shifted down by 1? Sorry, if 2x is different than 2, which one is greater, 2x or 2y, right? Which is basically the same as just asking if x or y is greater, right? Yeah. So I guess maybe the reason is because since those values are based off of the original equation, you need them to correctly work around 0. Maybe that's the best you can do. Billy Delsky. I'm sorry we decided to go with another candidate because he went to Harvard. If your hiring criteria for CS people is that they went to Harvard, whew, that company's going in the tank quick. I don't know. That's one to ruminate on. I think it's a fun little puzzle, right? And I don't know. You can also look up. This is a. I don't know if I'm spelling that right. I was kind of hoping they would have it minimized down to code so we could see what they get. What's RE? Ooh, whoa. So that seems bad. Like that does a bunch of multiplies there. I guess it's really just a shift by 4, which is fine. I'm sorry, shift by 2, right? I don't know what. This isn't that different from ours, I suppose. It looks basically the same, actually. This part I'm not so sure about. So this is assuming you only ever draw one pixel on like you can't ever draw 2 pixels upward, which seems weird. I guess you could say that because if you're just doing the top part, you just assume you never do that, right? So that seems like an interesting way to do it. Maybe, like, in other words, that's an optimization we didn't do, but like and I also don't know if it's an optimization you need to bother with, but basically what they were saying is like, look, either we're going to increment the y or we're going to increment the y and the x. So they basically did that, right? Which I think we could do the same thing, probably, although it might be we would have to maybe do it the opposite way around. I'm not sure which one we have our preference on, yeah. So if you were to do the y always, you could do that if you wanted to, based on the way we have it structured. I don't really know that you would care. On these old computers, you would rather just do it this way, I would think. But I don't know. Because I think you get a better, I think you get a better circle maybe this way, but maybe you don't. I mean, maybe you like that one better. So that's hard to say. But we don't really save anything by doing that, I don't think. And I feel like you need to do the update, like, you need to work the update back in so that you account for the fact that you're doing that every time, if that makes sense. Although it produces kind of a nice circle if you don't, which is kind of interesting. We should make our circle a little bit bigger. Just to make sure it still looks nice as a circle, but it does seem to. All right. I'm gonna leave that as an exercise for the reader to get better. It will get checked in. But I feel like this part here, it would really be interesting. Because if you look at how many registers it requires, to do this, it's 3 for these. Probably 5 once you do this. And maybe you could probably do it slightly differently, maybe, but I don't know. But then I feel like, and then 6 for this, I'm not sure what else you could really do. I don't see a lot of other stuff there. Because this is really what's going to kill you. This part here is now pretty free compared to this. This is just brutal, right? Because look at all these integer multiplies that have to happen. You really don't want those integer multiplies in there on these old machines, right? That's really, really bad. So I really think this is the most important thing to address, and I'm not sure how to best address it. Is there just a register? Here it is. So the 386 definitely had the 32-bit stuff, which we surmised. I don't know if the 286 did or not. But it does look like we would be super register starved. So we probably would need to do better than what we're doing, right? It just... Let's take a look at the 286. surely there is some... Surely somebody lists the registers. Come on, WikiChip. You can do it. Maybe WikiChip can't do it. There it is. Wow, so, okay. There's like no data. So it looks like it's the same as the 8086, maybe? Well, so interestingly enough, maybe we can have 4 of these. So maybe what we could have done is use 4 registers total by being clever. And then maybe if we really do have 4 address registers, we can use those for doing the 4 drawings, and then it would work. Maybe. I don't really know. So, I don't know. This would be an interesting exercise to basically go rework this routine on an actual 286 emulator, right? With like actual 286 assembly code. Although I guess you don't really, you know, I mean, there's like DOSBox, right? Like you could take this, right, and you could compile actual ASM that actually draws, like you could do mode 13 or something, or any graphics mode really, or just do what I did where you use the console. And see to get like to see what you can fit in here using only the registers available, right? Because that would be an interesting exercise, I feel like, to make work, and just see like whether or not there's good ways of doing this stuff. Because this looks brutal, and like this is definitely like... I think that's really the place. All right. So this episode of Handmade Hero is probably never going to actually be an episode of Handmade Hero. Sorry, folks. We've just gotten too far off topic. This will have to be a Handmade chat instead. Sorry. Hi, Casey. Sorry, it's pretty long and has nothing to do with circles. I'm a mathematician trying to be a graphics engine programmer. I made some pet projects using OpenGL and Vulkan in which I was able to make the things I wanted, but since my lack of enough experience, I had a hard time figuring out what professional programming is. I started watching him in December from day one and almost caught up. Currently day 520, thanks to amazing series. It has been ink, and then it got cut off. Well, I'm very glad to hear that. I don't know if that was a question. If there's something I can answer for you, please let me know. Otherwise, thanks for the kind words, as always. It's always great to hear people who can use the series to get them where they want to be, you know? I don't like... So does Twitch... Is it Twitch or Hex Chat? Who is clipping off... Like, sometimes that happens. Someone types in a long question, and it gets, like, truncated. Who is doing that? Is that Twitch? Does Twitch only have, like a Twitter-like limit on the number of characters that get entered? Because, like, I only end up seeing... Like, if I look in Hex Chat here, I only see part of it. You know what? Let me look over in the Twitch chat window. And see, does that happen in there as well? Yeah, so it happens in Twitch. So Twitch chat just basically just poops out at a fairly low character limit, probably because they were trying to avoid like spam and stuff. But I mean, we should probably put up like a little PSA that's like, hey folks, when you ask questions, if they're long, like break them into multiple chunks, you know? Because yeah, I looked in Twitch chat and it was truncated there too. At least on mine. Okay, so there's the question. Do you have any advice about starting a career in graphics engine programming for someone who has very strong background in mathematics, physics, can do research, perhaps can come up with creative ideas, wants to learn, etc.? I don't have a lot of advice about that because I don't really know what the best way to get into this stuff is. But you know, the only really thing that I've sort of said that I can contribute to suggestions there, because again, I'm not really involved. The only time I'm ever involved in hiring people really these days is if someone does something really, you know, obviously pretty impressive, I try to send them somewhere that you know, can make use of them, right? So I guess what I would say is the only thing that I would do that maybe if you're not already doing it, because, you know, I can't really give you advice about like how to make a resume or where to send it or stuff like that because I don't really know how those processes work. I would recommend going and listening to on Handmade Heroes channel. There should be so on here there should be a playlist for Handmade Con 2016. Yeah, here.
Writing's not.
And no, I didn't want an ad. Thank you. Let's see here. Just wanted to show someone where the stuff is. So this Handmade Con 2016 technical direction at Blizzard. That's probably the best place to look for just an overview of like how you generically get hired at like one of these larger companies to like start building a resume in the game industry. I would look at that. So maybe Google for Handmade Con 2016 technical direction at Blizzard. I would listen to that and it's only like an hour or something or 2 hours. So just listen to what he has to say. He's a technical director for World of Warcraft, so they hire people and they hire junior people occasionally, right? And he talks about how that pipeline goes. So you probably want to listen to that just to get that straight. But the other thing that I would suggest is if you have time, so if you are spending time, like you watch the Handmade Hero series, you've got some time, right? Because there's a lot of videos in there. Try to think of how to make something that people can see that you know what you're doing, right? So, you know, obvious, like, kind of above and beyond examples are, like, people who I've sent places already. Like, Alan Webster did 4Coder, right? He just made an editor and sent it to me. He's like, here's an editor. It replaces Emacs for you. Anyone who can do that is just useful, right? You know that if someone can just make a whole text editor from scratch in C, right? Not like we downloaded some rich text control and just wired it up to a menu, right? But like I actually wrote the whole thing. They're obviously useful. Like you can put them on any team and any good manager will be able to make them useful, right? Because they obviously have what it takes, you know, to do something useful on a team. The same was true for Nick Slivka, right? He wrote full debugger. I sent him to Rad because they were working on a debugger project. And I'm like, here's a dude who already made a whole debugger, right? The same would be true for George, but George already has a job. He's the guy who made the debugger we use right now. Same would be true for this program here, Milton. We haven't talked about it in a while, but it was actually done by I didn't actually know there was a... No, there really isn't. Never mind. Anyway, Sergio made Milton, and I don't know if he's got... I don't know if he has a page here anywhere. He might not. I guess he doesn't. Anyway, he made Milton, and it's like an entire drawing package that, you know, replaces a commercial one that we were using before, and it's just as good, right? So it's like, hey, this person is capable of making an entire commercial drawing package by themselves. When you get that much obvious stuff out, like when someone can just point, it's like, oh, this person obviously knows what they're doing, it makes it easy for someone like me, or, you know, any of the streamers like John Blow, whatever. If you have something that's obviously, you know what you're doing, then they can send you somewhere or hire you themselves, right? But people who are just like, I'm pretty good, but I have nothing to point to that shows that I am, it's a lot harder, right? Because then you're talking about, well, you know, no one's going to go out of their way to tell some other tech director or somebody to take a look at you, because they have no idea if you're good or not, right? There's no obvious thing to look at. And furthermore, like, as a resume thing, there's nothing that obviously distinguishes you from anybody else, etc. So I've always said, like, yeah, the best thing to do if you've got some time, make something that shows you what you're doing. Make a ray tracer, make asteroids, make a tool that people want to use, anything that you can think of to distinguish yourself. If you can do it, do that. That's the easiest way to show that you know what you're doing, is to actually accomplish something, right? And so that's the only really advice I think I could give, is if you do have the time to do something like that, do it. The other thing I would say, I've said a couple times, is technical blog. Blog about what you're doing. Write and show that you are thinking through these technical problems and that you are able to, like, work your way through them, right? It doesn't have to be the kind of technical blog that's like, let me tell the world about some new stuff they don't know about, right? Because you're not necessarily trying to say, hi, I'm the best programmer in the world or something, right? What you're trying to say is, I'm a good junior programmer, because that's all you need. That's the only threshold you need to cross to get hired, right? Because people hire junior programmers. There's plenty of places that do. So all you need to do is have a blog that shows, look, I am capable of working through these problems, and I can show that I understand them, right? And that is also another way to, you know, to have a concrete thing to point to that can differentiate you from the average candidate, right? So that's, you know, that's about all I can give you for advice, is like, try to do stuff that shows you know what you're doing, so that you don't just have to tell someone you're good. They can see that you're good, right? And you don't have to be better than a pro, because the pros already have jobs. You just have to show that you take more initiative and are more curious and harder working, right, than the average candidate, beginner, right? So that's I guess the best advice I can give. And whatever you can figure out to do that, that is the best thing to do. And then, you know, you can just show up on one of these streams, show up on John's stream, my stream, whatever, to say, hey, I made this thing, like, what do you think? If it's cool, and we'll look at it, right? And if it is, then we'll be like, oh, cool. And, you know, we'll say, oh, let me try to send you somewhere or whatever, right? But otherwise, it's just showing up and saying, hey, I'm like, I don't know, right? Like, I don't know, maybe you're actually really not good. And so I can't go recommend somebody if I don't have something to point to that makes me think, right? But so make it easy. Make it easy for the person to go, oh, this person's not the average person who wants to work on games or something, you know? Make it, the easier you make it, the more likely someone will. Just like everything else, when it comes to selling something, in this case, you're selling your job services, right? Just like anything else, whenever you're trying to sell something, the goal is to just make it as easy as possible for the buyer to say yes. And so give them every reason to think that you're better than the other people who are saying the same thing. And that's the best I can offer. For what it's worth, PCEM has cycle exact CPU cores if you want to be more accurate. Oh, that sounds kind of cool. I don't think I've ever heard of that. What's this? Oh, look at that. Well, that's just fun right there. On one of the first Handmade Hero streams, you said it was faster to work bitwise on a U in 32 than on a U in 8. Why? Did I really say that? I'm not sure what I would have meant by that. I can sort of say some things that could be meant by that. So, probably hopefully, if I wasn't just completely drunk that day or something, probably what I was trying to communicate was that in much the same way, like in the past I've said doubles are half the speed of floats, right? But what I'm trying to say there is the effective speed of doing what you're trying to do. So on a modern x86 processor, it's actually the same speed to do bit operations on a U8 as it is to do them on a U32. But doing them on a U32 does 4 bytes at a time. So any bit operation I'm trying to do, if I can do it on a full U32, it's 4 times faster than doing it on a U8, right? Because I'm doing 4 bytes at a time instead of 1. So I don't really know what the context was that I was talking about there, so that may have nothing to do with it. But generally speaking, anytime you can, like, modern processors tend not to differentiate much in terms of speed based on width. So doing something 8 bits wide versus 16 bits wide versus 32 bits wide versus 64 bits wide versus 128 bits wide versus 256 bits wide, well, not quite that at this point, but let's say 128 bits wide, they're all the same speed, right? And so if you can do your operation on a full 128 bits at a time, then that operation is just like fundamentally going to be 16 times faster than doing it on a U8 because you did 16 bytes all at once. Now, I don't know if that's what I was talking about or not, but that's really the way to think about it. Is if you have to do things a byte at a time, it's going to be twice as slow as if you did them a short at a time, which is going to be twice as slow as if you did them U32 at a time, which is going to be twice as slow as if you did them a 64-bit register at a time, which is going to be twice as slow as if you did a 128-bit register at a time, right? That's all really I was trying to say. And the same goes for floating point operations. It doesn't take probably much longer. I don't know, it depends. We have to look at the cycle counts. But for a lot of things like adding two floating point numbers together, it probably takes the same amount of time to add doubles as it does to add floats. We can look, but usually it's like roughly the same. But you can only fit 2 doubles into a 128-bit registers, where you can fit 4 floats. So even though the add takes the same amount of time, you did twice as many adds in the same amount of time, right? So it's still twice as fast. Now, in the future, that will go even higher. It'll go up to 256 or 512. But at the moment, like on any chips that I have anyway, doing operations on 512-bit wide registers are actually not as fast as doing them on 128-bit wide registers. And the reason for that is actually really complicated. It's not because they're double pumped. It used to be. That used to be true. And still is true on some chips. Like for example, AMD chips will like double pump 8-wide AVX too. And stuff like that. So it can be true. That can be the reason. But even when they're not double pumped, so let's say you have a full 512-bit wide chip, or a full 256-bit wide chip, it may still not be as fast as doing it 128-bit wide, and the reason is because the power consumption becomes problematic. So not all chips can run as fast through the 256 and 512 paths as they can through the 128-bit path. That's just reality, right? So you have to be careful making assumptions about the 256-bit wide and the 512-bit wide cases. It's not as straightforward as the 128-bit wide cases, right? The 128-bit wide case pretty much just runs at speed with the right power curve and everything's fine. 256 and 512 may or may not, and you have to actually like look at it to see. And also there's weird stuff. So even on modern like Core i9s, the latest Core i9s, I think. But takes with a grain of salt because my chip knowledge is wishy-washy. But I think even on the latest Core i9s, the chip powers down the 256 and 512-bit lanes when they're not in use. So there's even this extra weird penalty for using them, which is that you can't use them sporadically. If you're going to use them, you have to use them constantly so that it doesn't power down that part of the chip. Because if you hit them the first time, there's like a massive, it's like tens of thousands of cycle penalty or something like this to spin them up, right? So you can't just like use them and then not use them and then use them and not. You've got to like spin them up and keep them spun up or some weird nonsense like this. I don't have a lot of experience programming with the 256 to the 512 wide lanes for really hardcore optimization stuff. Largely because most chips just don't have that stuff, so it's not an issue. But any opinion of Linux way to define integer types with one letter, like U8, well, that's what I do. So in Handmade Hero, obviously I'm a fan because that's what I do. I don't know if you've been following along at all, but we do that. So these are the types that we use. So I mean, if you're just looking at my opinion, I like it. I used to use longer ones, like I used to use them this way, and I eventually just, even during Handmade Hero, decided I liked them even shorter. So we kind of went this. At some point we should probably just delete these and just go through and remove them all. But it's not a big deal. But I do like the short ones. I didn't know that was like a Linux way of doing it. That's how like Jeff does it at Rad. That's really where I got it from. I don't know the Linux part of things, but. Pug with a gun needs to be an enemy in the game. Yeah, we could. I wouldn't be averse to that. Someone wants to put it in the GitHub. Someone wants to file a bug in the GitHub for a feature request. For a program for Windows only, is DX the better OrbGL? DX is. It's just better supported. So if you're only shipping a Windows code, you definitely want to do DX. Generally speaking, I'd say you probably want to do DX on Windows these days anyway, not OpenGL, because you want to do like DX on Windows and Metal on Apple. You really can't do cross very well. What do you think of getting a college degree in information technology? Should you instead be working on hobby projects? My dad has been wanting me to get into a post-secondary school for a long time. I think the key is just whatever makes you learn and get better is the best thing to do. I didn't go to college of any kind, so I don't think it's necessary at all. But that's if you're the type of person who's like very self-motivated and learns on their own really well. And if you're not, then that isn't going to work, right? So I think whether or not additional schooling makes sense depends a lot on the person, And you kind of have to self-assess, right? You have to figure out like what's going to work best for you. I don't super find that college CS stuff is very good. It seems to be kind of crappy. So while it's better than nothing, it's probably not good for the working programmer. Like maybe if you're someone who wants to go in and like study church's thesis or something like that, then college CS degrees make sense. But I will say that like the quality of actual like coding behavior that tends to come out of colleges seems to be pretty bad. So there's that. Like there's probably some universities where they actually teach you how to program well, but I kind of get the feeling from my experience that most don't. Probably because most college professors don't really know how to program very well. That's not really their job. Like long haul hard work programming is just not what they do every day, right? They publish papers and like put together researchy sorts of things where the quality of the code is not really ever going to get tested particularly much. And the amount of output is very low compared to what a hardcore commercial programmer, what I expect from them or want from them. So it seems like the college style of programming tends to be more in line with what I see in like the 1,000 web programmers at Twitter and we don't ever seem to get anything done kind of programming, which is like highly theoretical, a lot of nonsense process stuff that doesn't really work, not very much output per programmer, not a lot of visible quality control, like that sort of thing. Just generally taking lots of people to do not very much, not very well, right? And it seems like they hire a lot along with college degrees, right? And so it seems like that kind of whole pipeline is sort of the same general thing up and down. So I don't think highly of that stuff. I really don't. But that's not to say that that's true everywhere, right? There's probably some universities where there are some professors who are very serious about programming, and those are probably the kinds of places that would churn out, as a product of their education, better actual commercial programmers. But that, from what I've seen, is not the norm. So, keep that perspective maybe in the back of your head a little bit. I've done lots of tools in C like string utility, JSON parser, data visualization on Linux using X11, vectorlib, and some other tools. Do you think these can be valuable for the CV? Possibly, right? Again, I would probably say I just give like vague advice. I mean, I don't know. It's been so long since I've tried to apply for a job in the game industry in the traditional way. Like, I mean, I never really did. So I can't really give good advice on that very well. All I can say is, imagine you were me or some other person with some connections who could recommend a person, right? So you're somebody who knows people who do hiring, and the question is, how do you get that, how do you get me to say, oh, this person seems to know what they're doing, right? And it's probably worth hiring as in an entry-level position. What am I going to go to your website and find that's going to make me think that, right? So it may well be that some utility you've already made could be that thing. If it's true, dress it up, make some posts about it, make it clear why it's interesting or what you did on it. Do you know what I'm saying? Let's say you were like, hey, I want to make a really high-speed JSON parser. So I started with my JSON parser, and I profiled it, and I did some back-of-the-envelope compilations to figure out what's memory bandwidth, how close I could get to that, like do a bunch of like blog posts on what's the fastest possible JSON parsing I could do or something, right? That's one good example. Another good example would be, how do I make a really good JSON parsing library? Here's me analyzing the API, looking how easy it is to use, trying a couple different variants, looking at the usage code, what makes the smallest usage code, how do I deal with the memory properly, right? Just saying as I made a JSON parser doesn't help me, right? I have no context for whether or not that person's good or bad. But show me something that shows you think through these problems, you work hard at them, you can solve real things, you know what the metrics are, right? Give me something to latch onto and point me at that. That's the key, right? So I don't know. Like, hopefully that kind of helps. I just don't know how to say it really any other way other than people like me are busy. We're doing stuff all the time. So, we're not going to spend a ton of time going and figuring out if some other person is good to hire or not, right? But if you can make it obvious, like if you can make it so that I want to go read your blog because I'm going to learn something, or it's just interesting what you did, or whatever, right? That gets you in the mix for free. You see what I'm saying? So just, I don't know, like put yourself in that headspace. Go, how do I make it so that someone who's busy, is not going to spend a lot of time looking at stuff, gets interested in what I did? Right? That's the puzzle you're trying to solve, fundamentally. That's the only real way to bypass that I just send a giant stack of CVs to everyone and hope the random people at HR who don't know anything about anything happen to pull mine out of the rabbit hat, right? Do you think it's enough to have a YouTube channel instead of a web page? It depends. A YouTube channel is sometimes a harder sell because someone has to actually set aside time to look at it. Like, keep in mind that most people read most stuff on their phone or something, on the bus or waiting in line or while they're commuting, right? And so if they don't have their headphones on, or if they don't, right, are they really going to click through to a YouTube channel? How long are they going to watch it for, right? So, I would consider, how hard is it to put up something? Even Fabian, right, who has one of the best technical blogs in the world, he didn't bother making his own blog. It's just on some hosted sites like WordPress or something, right? So just do that. No one cares that Fabian didn't make his own website. Here, let me show you. He just needed somewhere to post, so he did. And everyone reads it because it's really high quality, right? Right? So it's just this thing, and here's all his stuff, and it's all really good, right? So, Fabian doesn't need to apply for a job because he probably has infinite people who would hire him if he wasn't already hired. But the point is, it's the quality of the stuff on the site that matters here, not whether you made the web page. So just do whatever, doesn't matter. WordPress, Blogger, I don't know. Go type in some random thing like best blogging site and just go there and put up the content, right? It's the content that matters, not that you made the web page. So you don't have to worry at all about that, just if it's good enough for Fabian, it's good enough for you for sure. Right? Oh, someone was asking why we were suggesting you look at how to do it under 286 because they were asking me about a Microsoft job interview question that I got, and back when I interviewed as an intern, and so the question is how do you draw a circle as quickly as possible? The answer nowadays has nothing to do with any of that stuff that I just showed. This basic concept of looking at x squared plus y squared minus r squared still remains because, hey, that's the equation for a circle. But the actual way that you solve it has nothing to do with that, right? And that's because you need to operate on wide registers now. So you need to be testing multiple things at once, more than two. And so you need to do things a little differently in order to draw circles quickly, right? So I've been using a language with function polymorphism similar, I think, to what John is doing in JI. Multiple dispatch on input types. I recently tried out different language types, not at all very common. How come not more languages have this? Is it hard to implement or other issues? I guess to be completely honest with you, I'm going to try not to be too overly negative, but my opinion is that most language designers have no idea what they're doing. And that is why things like double dispatch aren't a part of the language, right? Dispatch on types is just something that you can build n-dimensional sparse matrices for. You should allow at least the metaprogramming capabilities to do that. Any language that doesn't have that in 2020, which is what we're coming up on here, is ridiculous. Obviously, C++ doesn't have it because, as I've said many times, they have absolutely no idea how to design a language or even what the point of a language is. So I would say it's probably just incompetence. Right? That's not to say that it's that important of a language feature. I don't know that dynamic dispatch across multiple types at the same time is really that important for most programs. I think sometimes people think it is, but usually it's actually not. But that's not a reason why your language shouldn't support it cleanly, because it's not that tricky, right? So I don't have an answer better than incompetence. I think it's just incompetence. I heard JAI is close to beta release. Will you be playing around with that or leaving it until it's matured more? If I have time, I'll play. Look, maybe we'll play around on like a stream, at some point. When John feels like it's worth that, I would trust his judgment. Have you met the Amiga programmer like Bruce Dawson? It seems they were great programmers. I'm sure Bruce will be happy to hear that. Yes, I do know Bruce Dawson personally, amusingly enough, because he worked actually at Cavedog, which was right over in Woodinville. And then after Cavedog, he went to Microsoft first. Anyway, then he ended up at Valve, and now I think he's at Google. So he's always kind of been around this area, actually, in recent years. I think he might have been Canadian originally, which is why he worked at Cavedog. I think he might have known Chris. Maybe that's not true. I can't remember. I can't remember how he knew Chris Taylor, or how he got hired there. Maybe he knew Ron Gilbert. I don't know. I don't know that part of his backstory. But yeah, I love Cygnus Ed. That was a great achievement in text setting for sure. Bruce is an optimization kind of person. I have met him, but I haven't really worked with him. I don't have a lot to say about him personally because I don't, I've never really worked with him on that stuff. But I have met him. Would you use sine and cosine now? No, you pretty much never want to use sine and cosine for things like drawing a circle, at least not that I can think of, unless what you're trying to do is actually compute like points on the circle, right? So if you're trying to rasterize a circle, you don't really need to skip along it. So if I'm trying to produce like points along a circle, sure, I'd use sine and cosine now because that's really the only way to do it that I can think of. But if you're trying to just rasterize it, you can still just use implicit function evaluation for that. So you usually do. Are you going to push the circle solution to good code? Yeah, it'll automatically go into the source code control because I put it in the MISC directory, so it should just be there. Do you ever use any scripting language? Not if I can avoid it. I don't really like underpowered languages very much. Is there any computer world outside US? I'm not sure what you mean by that, but if you mean are people outside of the United States making important contributions to computing or running large companies that do important projects, the answer is like absolutely yes. I mean, so much so that if you look at things like Grand Theft Auto 5, the most profitable game in history, that's a UK development-based organization, although it kind of have stuff all over the world. You can look at The Witcher, developed, I want to say, entirely in Poland. Is that correct? One of the biggest engine projects in recent history, right? There's Unity. That was originally developed outside the U.S. as well, although they have plenty of U.S. offices now, right? But not U.S. I don't know where most of like Ubisoft's development happens now, but like Montreal, like Canada, houses at least very important parts of like the Snowflake Engine studio, which does I think that's done in Montreal, and I think it's what's used for like the Division and stuff, right? Things like this. And then I know they've got like offices in France as well. There's Crow Team, right? The people who made both Serious Sam and the Talos Principle. They're in Croatia. There's, I mean, and these are just off the top of my head, right? And so, at least in the game industry, obviously tons of people all over the place. At the risk of stating the obvious, the PlayStation, the Nintendo Switch, these are originally Japanese companies. Obviously, the PlayStation 4 mostly made in the US. PlayStation 2 and prior, a lot of that stuff was Japanese-based. Nintendo, always in Japan for most of their stuff. Although, again, the Switch is now mostly US because it's like an NVIDIA Shield, basically, right? But, I mean, Super Mario Odyssey, Breath of the Wild, these are Japanese-oriented development projects. Obviously very important to the latest generation of games. And there's tons of, Capcom. The Japanese game industry is obviously, shouldn't need much introduction. I mean, hopefully most people are aware of what's going on in Japan game-wise. So there's a ton of stuff happening there. I'm less familiar with, like, Chinese and Korean game development, but they've got a ton of it. A lot of MMO-based development happens there. Obviously, PlayerUnknown's Battlegrounds developed in Korea. There's a bunch of MMOs that I don't really know personally much about. I can't remember all the names of them. They're like Black Sea, Black Pearl, something like that, was a big one. There's obviously a bunch of web companies in China, like, there's like Baidu. Line is like the Asian equivalent of things like Twitter or Facebook sorts of things. I think they've got over there that we're just totally... Oh, Black Desert, is that it? Anyway, I don't know a lot of those because I don't play MMOs. I'm really ignorant about that segment of the market. And obviously, since I don't speak fluent Chinese languages or Japanese, like I can't speak Mandarin, I can't speak Japanese, I can't speak Korean. I don't have a lot of experience on their like instant message platforms or social network sites, but they're all there, right? So there's tons of work going on everywhere. South America is, it seems like less influential at the moment, but gaining ground. There's a lot of game developers sort of starting to do work in South America that's becoming more relevant, right? Game developers in Argentina, right? Like Daniel Ben-Mergui, for example, who made Fidel Dungeon Rescue, which is a great game. Argentinian, developed in Argentina. And there's game industry stuff developing down there. It's just I don't know of anything big to point to. Like I don't think they've necessarily had like the crossover hit where I can point to something you would have heard of in the US that was developed there. But I might just be missing it. But it's starting, right? And so I feel like you give it time. Things take time to get enough talent, to get enough experience in an area to make like a breakout hit or whatever, right? So that's one. Obviously, there's tons of programmers in Russia, India, I just don't really know what they're working on. I'm sure there's stuff. I just don't know what it is, right? I don't know of any like big games to point to that came out of Russia or India, but there probably was. Probably a lot of contract work happens there too on other people's projects, right? Like a lot of places have like subsidiaries there that do work on them that you might not have heard of necessarily, but right. And then I'd also point out like Israel is a great example of a place that has tons of computer stuff. First of all, Intel's Israel operation was the people who developed like a lot of the core stuff you use in x64 chips today, right? Like the Pentium, like the P3 core was entirely them, I think. I don't know how much of the modern core is them. Probably a lot. They do a lot of work in Israel on the cores. Obviously, I think Waze was developed from Israel, like the mapping thing, which is very popular now. I don't know all the things that are developed in Israel, but there's a lot. So that's another hotbed of development, both hardware and software. I don't know much about the Middle East more broadly, like, you know, Iran, Iraq, Jordan, Qatar. I don't know offhand of much that comes out of there, but you know, there probably would be Dubai. A lot of those places are wealthy. They probably could have a software engineer. I don't know if they do. Singapore has a large. Had a large push for game developers at one point. I just don't know what came out of it. I think LucasArts might have located some people there. I don't know. I would suspect Singapore's got some. I'm sorry, I jumped from the Middle East to Singapore all of a sudden. It's not that far, I guess, but it's not really the same area. But I know that Singapore's got a large tech push. I just don't, again, know of what comes out of there exactly. Some people in the chat probably would. Does anyone know if Israel has a large English speaking population? Yeah, like most of Israel speaks English, right? I would assume that like, I mean, I could be way off base here, but I would assume that Israel like is pretty much English as the official language, and probably also maybe has like, you know, Hebrew or something as a cultural language or something like this. But I'm pretty sure Israel would be mostly speaking English in any tech setting. That would be my assumption. I would assume that most Israeli tech people are pretty much using English most of the time. That'd be my guess. Germany, I'm sure, is also another place that I can't think of off the top of my head, but you know they'd have a ton. Italy's harder. Can't think of much. Like Italy, Portugal, not sure about. Spain, definitely. They make Maxwell Render, for example, I think, in Spain. So I think they have a fair number of like CG things there. Already hit Poland. Turkey, I don't know. This is turning into a giant like world tour of game development, right? Is CryEngine from Germany? Maybe. Oh, Crytek is German. Okay, so Crytek is German. There you go. So, I mean, I don't know. I'm the wrong one to ask. I don't keep tabs on, like, the entire world of gaming, right? But what I can say is that while I don't know if everywhere in the world has tech development now, it's pretty close. Like, I mean, you can see just those are things I can name off the top of my head, and I don't keep track of it. So lots and lots and lots and lots of places have computer stuff going on right now. And some places don't have much, but they probably have a little bit, and a lot of places have a lot. Increasingly, I would say, in game development, a lot of it, the important stuff, is not happening in the US, I would say. You know, of the engine development that happens in the US, it's probably the minority of engine development happens in the US now. So a lot of it is extra US, in my opinion. again, just thinking of the engines, right? Um, Snowflake, I think is what it's called. I can't remember the name, the engine name for Ubisoft, but that's for sure not U.S. It's Canada. Crytek is Europe. Whatever the Rockstar engine wants to be called is Europe, right? I'm 99% positive that that's not much U.S. It might be they Rockstar San Diego. Maybe they collaborate. I don't know. So it's at least half not U.S. Let's put it that way. But I don't know their exact breakdown. Unity is not majority U.S. Although again, I'm sure they have U.S. development, but it's just not mostly. Frostbite, Sweden. We never mentioned that one, right? DICE in Sweden. So, of the engines that are developed entirely in the US, I'm trying to think of what they are, but like Unreal Engine is obviously an important one, but I don't know. Someone was saying that Rockstar San Diego does most of the engine. If that's the case, then maybe that is a US engine. I don't know, right? But a lot of the engines not done in the US. They're done elsewhere. Europe, Canada, Asia more broadly. So. I saw some codes that use the array of function pointers in enums to avoid branching. Enums like action type, move right, move left, and then function pointers associated with them. Do you think it is a good idea to do that? So I guess what I would say, and I'm kind of I guess what I would say is, honestly, I just don't know. So the reason I don't know is because while I know a fair bit about what happens to branches on Skylake on modern x64 cores, to be honest, I have really not studied call much. So I don't know what happens with a dependent call instruction. It may be that a dependent call instruction is always worse because it cannot be predicted, so it will always stall. Or it may be that that's not what happens, and so it's not always worse. This is something I probably should know these days, but it just never came up. So I can't really tell you. I can't really tell you. I should go read about exactly what happens in Skylake on a call. So let me give you some perspective on why I'm reticent to answer that question without actually studying it first. See if we got a diagram here. All right. So we haven't really talked about any of this stuff on Handmade Hero, largely because it's not the sort of thing that I work with typically, so I'm really the wrong one to teach you, but I'll do my best. If you look at a diagram for how an actual core of a modern x64 chip is working, you know, it looks like this. This is the one for the processor that we're on right now, a Skylake era processor, right? I think this might be a Coffee Lake chip, or maybe it's a Kaby Lake chip. I don't. What are we on right now? It's a Kaby Lake chip, which is basically a Skylake chip. There's not a whole lot of difference between the two. At least not that we know about, right? So anyway, this is what it looks like for the chip to actually function. And if you look at how it's broken down into a couple discrete parts. And these parts are about different things you do in order to produce the results of the assembly language. So you have to remember that in the old days, if you looked at assembly language, you were more or less looking at exactly what the processor was going to do. So if you took like the Commodore 64 or something, right, or an Apple II, if you looked at the assembly language, that was more or less a direct mapping into like what the hardware was actually going to do. So you didn't have to think too much about what was going on in the chip. Reading the assembly language would basically give you what you needed to know most of the time about what was going to happen. That's completely false for modern chips. And the reason it's completely false for modern chips is really twofold. You might even say threefold. One is that they actually don't ever execute those actual instructions. What they do is they break those instructions into smaller things called micro-ops that then get executed. And so any given instruction may translate into one or more micro-ops, and it's the micro-ops that actually tell you what the chip's going to do. There's thing one. Thing two is they don't have to execute those things in any particular way. They just need to guarantee that the results are the same as if they did. And so they get a lot of extra speed out of doing completely arbitrary reorderings or modifications to the things that you tell them to do. And thing three is there's a big old memory latency sitting on top of everything. So there's all this caching infrastructure to try and make that memory latency go away. And none of that was true back in the old days. In the old days, the memory ran at the same speed as the chip, right? On like a C64, I'm pretty sure that like you could access one piece of memory every clock cycle, and the instruction could only access one piece of memory anyway, so you were like done, right? And you know, I was never a C64 programmer, so take that with a grain of salt, but for the most part, you know, there's probably some subtlety there still, because there always is, but for the most part, you just don't think about like, oh, I've got all these different caches that are happening, right? It was just like, no, there's just memory and the chip. The memory comes into a register, does something, goes back out to memory, that's it. There's no in-betweens. There's no stalls there. There's no, right? So because of those things, it's a lot different now. The first part, the entire front end of the chip, as they call it, right? This whole thing is designed to do nothing other than just figure out what you're going to execute. There's a giant, huge section of the die dedicated to nothing other than just figuring out what you might actually do, right? And so what's all that about? Well, it's got to take instructions from memory. The executable lives in memory, right? It's got to get it out of there. Well, in the old days, it just read the memory. Nowadays, not so much, because reading memory is incredibly expensive. So first, we need to have a cache for the code, right? And that's the L1 instruction cache, right? So first, we have to have cache control logic that pulls pages in from the main memory and keeps them around. Second, is, I just said, we don't ever execute instructions. We execute micro-ops, which are little tiny instructions you can put together to make larger instructions that actually occur in the instruction stream. We don't want to do the work repetitively to turn instructions into micro-ops because it's expensive, so we also cache the micro-ops. So not only is there a cache of the memory that says what the actual code is the programmer wrote, but there's also a cache of the decode of those instructions into micro-ops, right? So there's this whole process here. All of this crap is designed to do nothing other than dump micro-ops into a queue that can then be issued into the backend for actual use, right? This part of the chip also can do other things. So, for example, I want to say, I don't know where register names get assigned. So the register alias table is here. So if we believe this diagram, which I guess we should, this doesn't rename things. So I guess I'm sorry, I'm just trying to think here. If you, just to give you an example of what I'm thinking of. If you were to do an operation like XOR EAX EAX, right? Or XOR RAX RAX. If you XOR a value with itself, you get 0. So XORing RAX to RAX really just says that RAX is going to get set to 0, right? That's going to get handled specially. I just don't know by whom. So I don't know whether some of the things that happen in here are actually going to get done a little bit differently before they get inserted in the micro stream, or whether like XOR RX RX gets inserted here and then handled as part of the register allocation table, or who knows what, right? These are the places where that gets handled, so it looks like it gets handled here. So anyway. Ignore that for now. It's not germane to the question. I was just trying to think it through in my head. All right, so after we decode everything into micro-ops, then they all get sent down to here, right? Where they actually start to get worked on. The way this works is this thing right here, rename, allocate, retirement. This is the buffer where all the micro-ops go in. And we have to retire them in order. So they go into this buffer, and we can fit this many of them. But we can execute any of them in any order we want, as long as we only ever retire them from the back, right? When they go into this buffer, we actually make up names for the registers that have nothing to do with what the registers are actually named. So, for example, in here, you might see something that says, like, add RAX and 1, right? Which puts a new value in RAX. And then something that says, like, sub RAX2, right? That sub RAX2, those are actually working on different values now. Like they don't have to be RAX anymore. So if someone in the future says mov RAX7 to overwrite RAX, it won't have to wait for those other two instructions. It'll just give that a new name. Right? It will rename all the registers from RAX to some actual name that's based on how many internal registers we can store. So even though like the processor has nominally like 16 general purpose registers, that doesn't matter. What those actually are not registers, they're names for registers that the code needs to use to tell the processor what's going on. They're completely irrelevant for storage because the storage actually happens in here on way more than 16 registers, right? So that's what's all going on in here. Finally, we have a scheduler system, which is what's actually going to determine how the UOPs go. This is a nightmare, apparently, to build. Here you see the register file, 180 here, 168 here. So this renaming can rename things using up to 180 different general purpose registers or 168 different vector registers, like the SIMD registers. So again, you have 16 names for registers, but you actually have at least 168 registers, right, that you can actually have in flight at any given time. This is why it doesn't matter if you, like, if you have like mov rax something, do an operation on rax, write it out, mov rax something, those are not going to stall on each other just because they both use rax. It just gets renamed and off you go. So it's as if you had like an infinite number of those registers effectively, because by the time you actually get to the end of it, you'll probably have finished any operations that were using the early ones, and you keep going, right? So then we actually get to the ALUs that actually do stuff. They do the work here based on the scheduler determining what's available to execute at any time. And then finally you go out to load and store buffers, which communicate to main memory, right? All right. So if you think about what has to happen with branch prediction, what ends up happening in here is when we dump stuff down into this buffer where we're saying like, oh, we need to do these operations. At some point, what's going to happen is we decided, probably based on... I'm not sure how we actually tell this thing when we missed. So again, this is why I just don't know with the calls. But basically what's going to happen is we're going to be filling up things into the allocation queue, right? And we're dumping them down into this buffer, the reorder buffer. At some point, we're going to get to a branch instruction, and that, like a jump instruction, and that jump instruction is going to have been predicted in the decode to have gone one way or the other, right? So we will have decoded some stream based on the jump, either not taking the jump or taking the jump. If when we get to retiring that instruction, right, if that retirement goes, oh, crap, I'm trying to execute this jump, I have the predicted direction of the jump, taken or not, but the actual computation of the jump that I now have done and am retiring says to do the opposite, all of the stuff that I had pending has to be flushed because it's all wrong. See what I'm saying? So that's why a mispredicted branch costs you money, right? Costs you cycles, because I already did some of the work, and now instead of just flowing nicely right through that work and getting the peak throughput I'm expecting, I have to stop, get rid of it, and tell this guy to feed me a different instruction stream. That's the penalty, right? That process is the penalty. I think it's 16 cycles if you hit the UOP cache. It's 20 cycles if you miss it on Skylake, I think. Somewhere around there. Those are averages, right? And obviously, it probably depends on how big fill this buffer was, like how much work you'd actually done, how much work you need to do. I don't know. There's probably dependencies in there that's hard to say what the actual penalty will be in your code, but it's something like that. All right. So what I don't know, because I've never looked at it, is what happens during a call. So there's two things that could happen during a call, and I don't know which one actually happens. One is that the front end has a way of predicting the call. So if the call is to a hard-coded address, that's trivial. It's always right, because it can't change. If the call is to a dependent address, who knows, right? It would have to have a way of predicting what that address was in order to do it. If it doesn't have a way of predicting it, then it's just going to stall here until it can compute it. So it's, I think, just as bad as mispredicting a branch, because nothing can happen. You're just going to full-on stall the chip until somebody gets that number back, right? So all of this buffer, everything just goes like a train with the handle pulled. It just screeches to a halt, waits for everything to retire up to the point where we've got the actual address to jump to call to, and then we go, right? So if a call is that way, then I can't really see it being better than a branch mispredict, but maybe it is, I don't know. If on the other hand, a call does do prediction, then to me it seems like it's probably the same as a branch mispredict, right? But it may be that because it's only one mispredict and not multiple mispredicts, like a switch statement might be, maybe it's easier for it to recover from that than the other way. I don't know. So I just want to give you some background, right? Like, that's why I don't know, because it's subtle and you need to go find out what actually happened. You can't just make it up. Like, I can't just pull something out of my butt here. I need to actually know, because unless I actually know, I can't reason about it in any way. It's that complicated what goes on in here, and we didn't even cover like a lot of it, right? I just kind of gave you the bare bones version. So I don't know. Skylake call instruction. How does this work? So I don't know. Call instruction Skylake front end decoding. One of the problems is I never really know where you look for a lot of this information. The best way is to ask Fabian when he's not thinking about it too much, and then he'll accidentally just tell you the answer. But you have to do it like slyly so it doesn't annoy him. If he gets frustrated with you asking too many questions, then he might just not answer. So that's the best way. If you kind of trying to slide it in some way that he's like, go to dinner and like mention casually, oh, I wonder how the call is, and then he'll just tell you how it works. But so let's see. Maybe we can just find a place where we say call. Well, this is Adam, which doesn't help us. So, I mean, it looks to me, I'm going to go out on a limb here. This is probably wrong, but I'm just going to say it. It looks to me like indirect calls are just, they attempt to predict them. And they also try to predict the ret instruction by assuming that you didn't modify the return location, which is in most code going to be true. So the ret is probably perfectly predicted most of the time, but the call, it sounds like, is a prediction and is probably going to be wrong. So I guess what I would say is, unless you think that the place that you are calling it tends to call the same thing all the time, a call will still be suffering the same penalty. So the question is whether or not expanding it out into multiple branches would make the predictor more or less likely to be able to do a good job. It probably depends on how many different things there are. But anyway, it seems like my intuition is at least mostly correct, which is to say that a call and a branch are basically the same thing. So the question is, can you get, if you just assume up front, it's not very predictable. So my branch and my call, they're just not very predictable. Then the call is definitely worse if we only have one branch. So let's say I had two things. I'm going to do A or B. And I can either use an indirect call or I can use an if. I think the if is probably always better because there's just less work to do and it's still a prediction. Two ifs versus a call, harder to say. Three ifs that are unpredictable maybe starts to be worse than a call that's indirected because, right? So I think you probably have to do that timing because it's which one, the overhead of a call exists and it's mispredicted versus I just had some if statements. Does that make sense? So I just don't know how to make that an arbitrary rule. You probably can't. What you're going to have to do is profile both ways and see which one's faster, unless you just know that there's like 300 different possibilities. So the number of ifs we would need is just astronomical, right? So obviously, like, the call is going to win or something. Does that make sense? But if it's like close, I would say probably have to time it or assume the ifs are faster would be the two things I would say. Does that help? Hopefully that helps. Does that answer your question? I saw John implement a compare and swap intrinsic recently for lock-free multi-threading. Except for implementing counters and stuff, what is it useful for? Do I understand it correctly that it is only useful when the thread unsafe code task is small? So compare and swap is actually the building block of all asynchronous algorithms of any complexity. It's important to understand that the seminal paper is this. It's by Maurice Hurley from DEC. Basically, everything ever invented in computing, of course, came from Digital Equipment Corporation and or the employees thereof who then went to work at other companies. That's not really true, but it's sort of true. This will tell you, if you actually read and internalize at least some of this paper, this will explain why compare and swap. I won't really go over it here. But compare and swap is actually the most important instruction. Every other algorithm could be implemented with compare and swap, but of all of the multi-threaded algorithms, all of them can be implemented with compare and swap, so it is the uber primitive. Some multi-threaded algorithms can be implemented without compare and swap by using some other thing like locked increment or locked swap with no compare. But if you're only going to have one thing, it's compare and swap. That is the one primitive you can prove can do everything, and all other things you can prove can't do everything. And this is the paper that proves this for you. Hopefully that helps. And it has nothing to do with the size of the thing you're doing or the type of algorithm or anything. It's just a superset. So compare and swap does everything. Locked increment, locked swap, locked decrement, locked add. These are all worse versions of compare and swap that you can only use in certain circumstances. But sometimes they're better in those circumstances. So it's not that you don't necessarily want them for optimality, like speed, but they can't do as much. So in terms of capability, it is always compare and swap that you actually need. As for whether we use it in Handmade Hero, I don't know. We probably don't need it in Handmade Hero because we can probably get away with locked increment, but I don't know. We might use it compare and swap. I think we do. Why aren't we using analog computing instead of bits use frequencies? There are people who propose that. The reason I think is because that's just not what computing grew out of. Analog computers weren't the thing that caught on. Digital computers caught on early in like the von Neumann era, right? And there were people who proposed them back then and built them. So it remains to be seen. Maybe in the future, it turns out we switch to analog computing someday. I don't know. But there's something straightforward about saying we always clamp everything to like positive or negative, right? That allows you to, noise is a good example. It allows you to create reliable things that can be reproduced, right? And that's kind of a fundamental aspect of computing. So I don't know. I am 50,000 lines into a C++ Android engine development. Should I rewrite it the C way? How can I change my thinking? You at some point said that one should come to the point where OOP fails and you use the non-OOP, but I think I am not really there yet. Hope this is a dumb question. Yeah, I guess what I would say is you don't need to change programming habits if they're not causing you a problem. Now, sometimes things can be causing you a problem and you don't know it. That's a little bit tricky. But assuming that you're not, like, what I would say is, are you spending a lot of time thinking about how you're programming? And if you are, that's a bad sign, right? You should be mostly thinking about the problems you're trying to solve. And what happens typically with OOP programming is you end up thinking about the OOP-ness stuff a lot. If you see that happening, that's a good time to reassess. But if you're just not having that problem, you may not need to worry about it, right? So I guess that's the way I would think about it. Someone's saying, are you saying Fabian did one on branch prediction? Is this it? Okay, awesome. So I have not watched this yet. I will watch it. But I don't know if this covers the call stuff. But even if it doesn't, just probably everything in here is stuff you're going to want to know. Fabian, like, spends so much time working on these sorts of things that, like, he has a ton of knowledge about how the chips are actually doing what they're doing because he actually has to know, right? And so probably everyone should just watch this video. This is not the number of views that I would prefer to see on this video. Like, that should be like 10 times the number there, and I will be adding one to it later. So I would say, like, watch that video. It may not cover the exact thing we're talking about, but all the things that it does cover are things you will want to know. Right? I don't know if there's more in here. So this one on superscalar pipes stalls, that probably has it. Maybe. Again, one of the problems is these may not be super relevant to like x64 either. So he may not really answer your question directly, but just I'm sure these would probably be a good thing to get you in the mode you need to be to like think these things through. Because he'll be giving you the background you need to understand why it's not a simple question, right? Hopefully. So check out that channel. Maybe someone can link to it in this episode. I know Miblo often does a really good job of building links. So maybe link to this Fabian Giesen stream here, like this page of the videos, and just, watch these. It's like there's no playlist, but just watch these 4 videos. It'll probably be a very useful 8 hours of your time. It's probably got way more information density than 8 hours of Handmade Hero, right? Where we're mostly just doing programming stuff and occasionally go through stuff, but So I would give that a shot. All right, I'm gonna wind down. thank you everybody for joining me for another episode of Handmade Hero. It's been a pleasure coding with you as always. If you want to follow along at home, you can always pre-order the game on handmadehero.org. It comes with the source code, so you can follow along with it. We did not actually do any Handmade Hero today, so this probably won't. I will not actually call this day 533. We'll call next time 533, and this will probably go up as a Handmade chat on the YouTube archive. So, I'll be back next week when we're just going to start polishing the asset system and just plowing assets into the game, basically, trying to get that. We just want to turn the crank a few times on that, get the font stuff clean, get the ground cover clean, obstacles, decorate the world, just try to really start making it so that we need to go through and iron out every last little crappy thing that we did and just improve it to the point where it's super, super smooth to just put assets in the game. We've done all the hard work, and now we just need to turn that crank a few times. So we'll use the excuse of decorating our world to just polish all the pieces. It'll take us a couple weeks to do because we're going to want to really try and do a good job of simplifying everything down and cleaning it up and making it nice and really easy to use. That's what we'll be doing for the next few weeks. Hope to see you back here for that. Until then, have fun programming, and I will see everyone on the internet. Oh, and this week, go watch Fabian's videos. Watch those videos. And they will help you a lot understand what's going on in the modern superscalar CPUs that do out of order and all that stuff. All right, take it easy, everybody.